temperature outside is minus 30 degrees Celsius. You breathe that air in, and what is the typical tissue temperature? Maybe around 40 degrees Celsius. So that's a big enough jump. So I'm just curious if that is fine. So how much is 30 Kelvin converted to Celsius? Huh? Minus 240. So the delta is 240 Celsius approximately. So hence it is not possible. And I think if
the delta to 30 Celsius, each unit Kelvin is almost each unit equal to Celsius. So del P will be 30 degrees Celsius. Like if you take absolute temperature 30 Kelvin, that is minus 240. But if you look at the difference of the let's say 30 Kelvin difference, we can straight away say it is 30 degrees Celsius difference also. Because each unit is like equal to each other. Fahrenheit you have to like 1.8 Kelvin.
yeah, so I need to explore more on this. Whether I mean it is fine at regular temps, but if it is indeed that cold, that 30 degrees Celsius difference, I wonder, like when I go outside and do things, when I am really outside in that temperature, whether the tissues, like we are talking about the very outer tissue, right, inside the nose, whether they still stay at 40 degrees Celsius or not. Because I once heard this funny story, and it's a real story, that in the colder regions of Canada, which is similar to what we have in Brookings, like if you go outside, and in fact even in Brookings, like if I have a cold, the mucus coming out would freeze when I'm outside. And for that matter, if you take a shower and just go outside, your hair would freeze, because the water would freeze. So that is interesting. I did not think much about this temperature difference, but what happens in the extreme climate zones. But anyways, let's assume that it is incompressible and we can use the version of Navier Stokes that we have found out and see what we can deduce based on, for example, what the Reynolds number could be in a certain region of the airway. Okay, so as a brief recap, in addition to this, what we did in the first 2 days primarily was we tried to model particle transport. We started out with equations that are very idealized in any random geometry, and then we tried to see if we induce some kind of curvature which is inspired from the anatomical geometry. We induce certain sizes of the cross sections, what we can deduce in terms of the particle transport trends. And then towards the end of yesterday, we realized that yes, particle transport in terms of how the fluid field, the flow field talks with the particle transport is through the drag force, right? So if you look back at our calculations, you'll see that we assumed a realistic flow rate. So the drag force effect was more or less similar, even if it's a very complex geometry, whatever the drag force would have been in that flow field. But now that we are trying to think about the fluid dynamics in the respiratory tract, things are a little bit trickier. Because as we saw, like if you have a very complex topology of the domain, which we do have, topologically it is similar to a pipe. But a pipe flow won't have those different vortex dynamics features, for example. It will be straight streamlines or smooth streamlines. On the other hand, we do know that we come across this very strong vortex, coherent vortex patches in the inner flow field. So the challenge is slightly different here. The first thing that we are going to do today is non-dimensionalize the Navier-Stokes equation and see what we can tell by simply looking at which terms in the Navier-Stokes equation would be dominant. And as a result, that will eventually guide us what we would need to do in the full-scale numerical simulations, because analytical models can only go as far in terms of replicating the inner flow field. While modeling the flow field through numerics, we have to make certain decisions like whether it's an unstable flow field or it's turbulent or whether it's laminar. And those deductions could be obtained by what we are doing now, by looking at the various curves and looking at which terms are dominant. Before we start the simulations, the computational simulations tomorrow, I would still want to show you one case where I try to generate the flow field in an idealized domain, and the differences that we will see in terms of a full-scale model generated flow field versus the idealized flow field would tell us why this is probably not the best idea to idealize the geometry while trying to understand the flow field as such. The particle transport is fine, and as I showed yesterday, that last problem that we did with the MATLAB code on what is the density needed for a certain particle of a certain size to deposit, that is quite interesting, and it will be worth following up on that. Okay, so today let's begin with, so this is day 3. So non-dimensional analysis of the fluid dynamics equations. So we are going to assume incompressible flow. So let's write down the Navier-Stokes for that. So for incompressible flow, which is in this case the inhaled air flow, conservation of linear momentum leads to the Navier-Stokes equations. So rho material derivative of the velocity field minus grad of p plus mu Laplacian of v. So let's break up the material derivative, and I'm taking rho to the other side. So we have del v del t is v dot grad v minus 1 over rho grad of p plus mu over rho Laplacian v. So this is the dimensional equation. Let's now try to non-dimensionalize it. So we are going to pick a velocity scale here. Yes. Huh? We are not taking the body force right now. The body force would be, as we know, an added term over here. But we are not taking the body force here. The understanding that we are trying to get at, as I just was trying to let to you guys, is to figure out what are the dominant terms. So for example, if we see that the del v del t term, whatever that term is after we non-dimensionalize, if that is a dominant term, that means that while simulating the flow rate, we have to think about downside initial flow. On the other hand, if we see that that term is negligible, viscosity is dominant, we can possibly think about a laminar solution. So either way, whether you consider the body force or not, it doesn't make a difference. If you're trying to analyze the dominant terms of the equation, you can do that with the body force. Okay. Now for the velocity scale, let's use a slightly different terminology, u instead of u naught, that I was taking, because I want to make a clear distinction between what we have been doing for the first two days, which was geared towards understanding the particle transport, compared to now, when we're trying to understand the flow field. So let the velocity scale be u. So as a result, the non-dimensionalized velocity field V is V over U. Again, note that this V is different to the V that we had in the first two tests, where the V was standing in for the particle velocity. Here we are talking about the velocity in the flow field. There is no particle as such. Let the time scale be T. So as a result, the non-dimensionalized time scale is T over caps T. So we have taken care of the V, we have taken care of the time. So this T. What else is left if we want to non-dimensionalize this equation? The pressure. So there are actually two choices of pressure scales based on whether the flow has a high Reynolds number or a low Reynolds number. So the two choices of pressure scales, let's call that this P. So this P is mu U over L, where L is a characteristic dimension when we have a viscous domain primarily. So this is a viscous scale, and the Reynolds number is small. The other option for P is rho U squared when we have an inertial scale for large Reynolds number. So let's apply both into the dimensional equation and see what we get. So therefore, with the first one for low Reynolds number, P is mu U over L. This leads to Stokes number times del V prime del T plus Reynolds number V bar prime dot grad V is equal to minus grad of P plus del square V bar prime. Say again? Yeah, here. Rho U square by L. Some people take half rho U square. Yeah. Okay, so let's look at this equation first. So the Reynolds number being low, this is the convective part. So that is going to be negligible. And that is pretty much that we can enforce on this equation. So this part can be neglected because the Reynolds number is low. Now this is until now, and even if we do apply the inertial scale, which I'm going to do next, we are still not really connecting this to what is happening in the respiratory pathway. That is going to happen next. But as of now, if you have small Reynolds number, you can ignore the convective part. And just to think a little bit ahead on where you might come across small Reynolds number in the respiratory pathway, can you guys guess that Reynolds number is going to be small in our respiratory tree? No. The cross-sectional area is larger, but the flow is also quite fast. It is actually in the very final channels of the lungs. So as the air goes deeper, once it goes to the higher generations of the bronchial branching, that's where we encounter the low Reynolds numbers. And those have been studied experimentally. I'm going to come to that one next later on. But just to know that we have ignored the convective part, but we still don't know about the other terms in connection to the respiratory flow field. and there will be other assumptions that we can further place on this equation. Okay. Yes.
For the time we had used the convective scaling non-dimensional, that reduces the relaxation.
Say again.
Non-dimensional is the time.
Yes.
The scaling we have used is for the same as shouldn't it be a discussed time?
I have not said much about the time scale, have I? So it is just a characteristic time t. You can think of it as the relaxation time is inherent to the particle dynamics. We are not thinking about particle dynamics anymore.
But the slope number will come once we have the relaxation.
The Stokes number will come anyways, whatever characteristic time you might take. The Stokes number, what I showed is if you think of the characteristic time as the particle relaxation time, a part of it is the Stokes number. Right? So Stokes number times, but that does not.
T dash just for the sake of
Which one?
the Stokes number equation, T dash.
Oh yeah, right. That I missed. So this del t prime should be the. I have a bad habit of missing this prime.
No, so generally you can just avoid all the dash for the next to avoid any confusion.
I don't know if you guys noticed, I also corrected my notes because I missed this prime side. Okay, so this is for the low Reynolds number. Let's look at the large Reynolds number. So now this p scale is rho u square. So we have 1 over Struhel number del v prime del t prime plus v prime dot grad v minus grad of p plus 1 over Reynolds number plus n of p prime. So now over here, of course, the viscosity term, this RE being large, we can ignore that safely. But we will further develop this equation for the respiratory pathway to see what else we can tell about it when the Reynolds number is large, which is what happens when the flow is within the upper respiratory tract for sure to the larynx. It goes through a transitional regime through the trachea and in the conducting region of the lungs, which is still around generation 3 or 4, but still safely when I'm modeling the airflow till generation 3 or 4, I assume that it is a large Reynolds number regime. As I said yesterday, it is difficult to segregate from high Reynolds number to transitional regime in the same simulation. So this over here, just for clarification, because I myself always confused between Stokes number symbol and Struhel number, so this is the Struhel number. Okay, so let me write down some comments now in connection to the respiratory flow field on what the typical trends of the flow would be like in different regions. So it is seen that RE, the Reynolds number is quite high. Again, for clarification, I think in the first 2 days when I wrote RE, I probably could have used REP for the particle Reynolds number. This is the Reynolds number of the flow field. So let's not confuse between the day 1, day 2 Reynolds number with the Reynolds number we are talking about now. So it is seen that the Reynolds number is quite high in the upper respiratory tract till at least the larynx, and is very low when we enter the deep lungs. again in the community, especially when mechanicians like us are trying to model the fluid mechanics in the lungs, different people define what is deep lungs. So when I am saying deep lungs, I'm talking about the regions that are after the conducting zone of the lungs. So from generation 5, 6 onwards till generation 23. Okay, so when the flow is at high Reynolds number, which is in the upper respiratory tract, the internal flow become turbulent at the high Reynolds number. And as we go into the deep lungs, we can safely assume that the flow is going to be laminar, and we can control our simulations accordingly. And a laminar at low RE at the further recesses of the lungs. So since we are going to start the simulations hopefully yesterday for the upper and the central airway till the low bronchial generations, we are going to use turbulence modeling schemes. We are going to use large eddy simulation in our work. We are not going to simulate anything for the deep lungs, at least in this course. But if you do, at least the benefit would be you don't have to worry about using turbulence schemes. You can use a laminar viscous model. Okay? Okay, let's now look at further evolving this second equation and see what else we can derive from here. And the reason why I decided to use this particular equation is because I came across some experimental data where they looked at the ratio between the Reynolds number and the Strouhal number, so RE over ST. And if we can bring the RE on the left hand side, of course that is trivial, but we can correlate that form of the equation with what we see from the experiments to enforce some more conditions on this equation.
So let's typical physical magnitudes of the velocity in the bigger pathways of the lungs.
So yesterday in the problem I assumed 5 meters per second. That's a good question. Let's do a quick calculation. So for example, if you think about this particular geometry, what do you think the cross section should be, the area as a nostril? Maybe 2 centimeters by 2 centimeters. So if I pitch the area to be 4 centimeters square, and the flux, as I said, for relaxed breathing or even for moderate breathing, the Q is 15 to 30 liters per minute. So let's pick the mean to be 20 liters per minute. Therefore, the V is going to be Q over A. Give me 20, convert 20 liters per minute to meters per second. How much is that?
So liter is like 1000 cc.
This person is perfect. I cannot use the internet. 0.83 meters per second. Four centimeters square to 4 meters square. To 2 meters square. How much is that? Huh?
This is velocity.
This is the velocity. Okay. Okay. So 0.83 meters per second.
This is meters per minute.
Are you sure about the
calculate? 20 into 1000, that will be 20,000 cc per minute. Then you divide by 60 into 4.
20 liters is 1 liter is equal to 1000
cc.
Okay, let's give me the correct number or confirm number. Huh? 0.083? 0.83. Okay, he already gave me that number. Someone else confirm if it is indeed that? 0.8. Okay. So, where do we stand in terms of that? So, this is just the flow rate going in, the velocity going in through the nostril. Where was your question coming from?
What is the velocity, like magnitude in our upper pathways?
So, let's assume that this is on the order of 1 meters per second. What we had assumed was 5 meters per second. Now, I have to check the cross sections as we go further in as things get narrower, and that can probably, if it gets wider, that would make it more than this or bigger than this. But the order is still going to be the same. So let's assume that it is on the order of 10 to the power 0. But the good thing is, while trying to simulate this flow conditions, we gathered, and this is a few years back, around 5-6 years back. So we have this breathing apparatus that the person is supposed to breathe in and breathe out, and we collected the flow rate speeds in real subjects. And there is an empirical formula as well, which I'm going to show before we run the simulations. So whatever flow rate we would decide to simulate eventually. So even to complete the problem that I proposed yesterday, we just tested 2 particle diameters. We can apply the realistic breathing rates. I'm getting more curious. Let's quickly take a look at the problem that we solved yesterday. So over here, the A was the tau Vf square over L naught. So this, if we change it to, so if you think about this to be 1 meters per second instead of 5, so this becomes around what, 3 point, no, rho Vf squared. So let's do this calculation later on. So what happens if you rather take it as 1 meters per second? In fact, let's do it now. Why don't we do it now? We have time. So let's go to this. So we had A as tau Vf square over L naught. So let's just pick the 100 micron case. You can go back to your lecture notes yesterday. Let's pick the 100 microns case. We saw that tau was 0.031. So let's use that. So this would be 0.031 times, we are now picking it as 1 meters per second as the velocity, divided by L naught. And L naught was 0.05, right? How much is this? 0.62. Okay. Anything else that is changing in the main equation? We have the equation was tau Vf square over L naught times t plus tau e to the power of minus t over tau minus 1 minus L is the equation that we were trying to solve numerically. So tau Vf square is now 0.62. The relaxation time stays same. It is not dependent on the flow field, right? So let's revise the value now in the code. So this becomes 0.62. V was the relaxation time, that's just same. So let's run this. So what did we have before? We had before, let's go back. So before, the solution for the time interval was 0.0046. Now we have 0.62, 0.0254. So it did change as we expect that it would change. But still, it is small enough that it's clear that it's going to be positive in the forever. So that tells us that once we become more precise, this was just an estimate, right? When I plugged in those numbers for the velocities and whatnot. But once we plug in the real numbers, this could be a valid project that anyone here can solve. Okay? Any questions? Okay, let's go back to the document viewer. Okay, so as I said, we are trying to utilize the experimental data. We are going to modify this equation a little bit, basically get Reynolds number to the other side. So let's reformat the second non-dimensional equation. So therefore, Reynolds number over Strouhal number del V prime del T prime plus Reynolds number is equal to minus Reynolds number grad P plus Laplacian of V prime. If you guys are looking at the lecture notes, I see that I made a mistake of skipping the prime on the time. So if you see that and it is obvious that it's my handwritten typo, just correct it on your own. So now let's look at what we have from the experimental data. And since I'm drawing it by hand, it is going to be a rough sketch, but you'll still get the generic order of magnitude. So I'm going to start, so on the y-axis we'll have Reynolds over Strouhal. It will start from 0.0001, then 0.01, then 0.1, then 10. And on the x-axis, we will have the bronchial generations, but we will start from where the larynx is. So we move from the upper respiratory tract deep into the lungs. So the values they start from around 10. Let's note down this as well. So 2, 3, 4, dot, 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 till 20, 22, 23. So they go like this. So this is the generic trend of the RE over ST. So as a result, now what we can tell about this main equation. So when we are still in the laryngeal region in the upper respiratory tract, this term is big enough. That means the unsteady component is still significant enough. But as we go further in, the RE over ST dies down, which tells us that the unsteady term could be ignored while simulating the flow field. But what else is happening? We know that in the upper respiratory tract, Reynolds number is large. So these terms would still be there. The convective term would be there. The pressure term would be there as well, of course. But as we go further in, we also know that the Reynolds number dies down. So then this convective term goes to close to 0. This term would also go close to 0. And we will be left with just the viscous term, essentially, in the equation. So let me write these comments down. So in the upper airway, the Reynolds number is large, and so is the RE over ST. So as a result, both the unsteady and the convective components are dominant. Okay. So let me just, for the sake of clarification, this is experimental data. The unsteady term, the convective, and the viscous. So while modeling the airflow, we have to assume that it is unsteady, the flow field, and simulate it accordingly. When I first started out in this track of research as a postdoc, because I was working in a group where probably I was the only fluid mechanician, so there was this understanding that it is okay to model the flow as laminar, even if someone is breathing at say 15 liters per minute, which is what in the clinical world they assume it's relaxed, steady breathing when someone is sitting down. And I did model them as laminar flow. And some of those works also have been published. So probably that was not the most Puritan way to simulate if you think about the fluid mechanics of the system. And the second error that I did, and these things we learn over the course of years, right? Eventually I realized that things are turbulent, so I started modeling them as Ranks models. And then I realized that the vortex features are very important in this flow field. And those happen over very short time scales. And what Ranks does is averaging, right? So it does get something, but that is probably not what is physiologically realistic. So then we had to, by then I was done with postdoc and I had my group at SDSU and we tried to gradually move into validity simulation. So nowadays, all the papers that you will see coming out of my group, they use typically, as long as we are in the upper respiratory tract, the LES simulations. Okay, So this is for the upper respiratory tract, which is what we are going to simulate in this course. In the deep lung, the Reynolds number is small. Therefore, along with the fact that from the experimental data we see that the first term goes out, the second term would fizzle out as well because the Reynolds number is small, so there is no convective component. So therefore, the convective component is small, along with ignoring the unsteady term, because RE over ST is small. So RE over ST, if you take half of it, what is that? It has a name, and I'm sure you guys use it more often. Many of you might use it more often than even I do. Isn't it the Omersley number? That's what I figured out. It's the Omersley number. So it's the Omersley number. So this gives a measure of the importance of the unsteady term in comparison to the viscous term. So as and when you guys write papers for this kind of systems, I think, especially if you are going to venues where fluid mechanics is what people are worried about, you need to justify what you pick for your simulation parameters, and this is one way to do it. Unfortunately, I did not note down the citation for this experimental data. If you are interested in the future, just let me know. I'll take it out.
So,
Yes.
so for the low RE region, that we should look at the first non-dimensional equation instead of taking this.
I decided to use this because I had the experimental data. Now, if you do take a look at you are right. So if you do take a look at this first equation, what happens then? So you can ignore the convective term. What else are we doing here? So the Stokes number, we know that as we go further in, the Stokes number is related to the Reynolds number. So that unsteady term would go down as well. So eventually we'll reach the same conclusion, even if you use the first equation. I decided to use the second equation for both the regimes just because we have this support of the real physiological data to compare against. Okay. Let's do this as well before we stop. Okay, so you guys have the printout for this. So this is coming from a work from my group that has not been published yet, but it's on archive and it is going through peer review right now. Uh, since the projector is not very thin, why don't you open it up? So here what we did was, it is exactly this by the way, finally what we were saying here is the exact same model as this one. So we simulated inhalation through this geometry, and this is a 30 liters per minute simulation using LES model. The thing that I want to point out is the secondary flow features that are popping up in this domain. So the secondary flow patterns, and this is 30 liters per minute inhaled airflow. Now, going by this little calculation that we just did, if we had picked 30 liters per minute, this number would have been a little higher, right? So probably a little over 1. Now, if you think about what is going on here, it is 30 liters per minute. The flow is not only entering through the nostrils, it is also entering through the mouth. So the flow is getting broken up. But still, if you look at the range, it is fairly thin in that zone. And then we are in that kind of region, the values that you guys calculated. But as we go further downwind, things are getting trickier because now all the flow is getting merged into these very small cross sections. To get an idea about how small the cross sections could be with this frame, so which is it is somewhere over here, basically. So this is how tiny it is, and it is taking to 30 bits per minute flow. And as you can see, the cross section lies even within this kind of penetrative depth. So the first one is the velocity field, the second one is the pressure field, the third one is the vorticity magnitude. Now the interesting thing is, since we are talking about the secondary flow patterns, is to forget the first two for now, focus on the third one. We see that there are some vortex regions in the upper respiratory tract, like if you change the range of the
So here we have only taken the positive, just the magnitude.
just the magnitude. So it's the magnitude
Mod.
the resultant of omega x, omega y.
But if we take like the absolute means instead of absolute magnitude, if we take both positive and negative, isn't it better like we can show the different patterns like something in negative positions will show that the flow is going in the other direction.
Yeah, we have been thinking about that whether we should do that. The thing is, the reason why I took it is because at the end we were trying to study how the vortex regions are impacting the particle transfer, right? And as it's not here yet, but as I will show, we were trying to develop a 2D idealized reduced order model where we can use this vortex magnitude as the strength of the quantum vortex. Right? So when you collapse everything to a 2D plane, if you use omega x, omega y, omega z, you can still do that. But the thing is, if you think about the direction of rotation for each of those vortices, we have so over here, if you see the axis, y is up, z, and then x is going into the screen. So omega y would be like this, right? And omega z is like this. So let's first focus on omega y. It is giving sort of like a swirling motion. The particle is going in. Now whether that omega y can do much to the particle, it would do. It can do some to the some effects, induce some effects on the particle, but can we capture that effect on a 2D model? We cannot, because we are restraining the motion of the particle on that 2D cross section. So we could not really just use omega y because then it would be misrepresentative. Similarly for omega z, it can move the particle around like this, but then again we are doing a 2D model, and if we just pick omega z, then also it will be misrepresentative. Omega x is fine because the 2D model is like this. So basically, I'm looking at a rectangular domain which is equivalent to this. The omega x is going to move it towards these walls, but then if we don't include the effect of the omega y and omega z, then also that effect is introduced. So the best possible solution that we thought in terms of replicating the vortex induced effect on the particles would be to take the effect of all the three components.
You taking a root mean square of omega x square over 2 is happening.
You can directly output the velocity magnitude.
Oh.
Yeah. But to your point, if you are rather, instead of the plane being on this plane, if you are looking at a plane that is cross-stream, then perhaps you can think about other magnitudes, but then again you have to restrain the particles on that plane, which is tricky. Does it make sense, what we are trying to discuss? So that's why I picked the vorticity magnitude, but this is a very new line of research in the sense no one has looked at reduced order models of this kind of systems. They have been simulating this kind of airflow for the last 10 years, and you'll see plenty of work where they're just using the commercial simulation packages and reducing different things. But understanding the flow field, what is going on, is still not there that prominently. And without that being there, whatever you have is just a set of numerical experiments, right? So this, and this is something that we will ask all the time. So this works for this particular subject. What about someone else? So the holy grail over here is to figure out some kind of generic trend. And to extract the generic trend, you need to think about a little bit on what you can derive analytically. And that's why we are trying to go towards a reduced order model, which I'm going to discuss a little bit in this course later on. But for now, let's focus on the secondary flow patterns. So since we were focusing on the vortex formations, over here, yes.
Pressure computation. This pressure is like minus 50 pascals. Is it like base pressure only we have?
This is absolutely right. Don't worry about the atmospheric pressure as such. We induce zero. So basically,
Gauge pressure, right?
gauge pressure. So the 0 pascals was at the opening, the inlet openings, and that's why it starts from red over there, and the negative pressure drives the flow. So basically, gauge pressure, delta P, whatever you call it. Okay, so we are focusing on the vorticity magnitude. So here is just a zoom in visual of the third diagram over there. And to your point, that F, G, and H are the X, Y, and Z components. So to your point, the panels F, G, and H, they are the omega X, omega Y, and omega Z. So as you can see, the omega X is small, omega Y is slightly bigger than omega X, but still small. The main driving thing is omega Z. But if we just use omega Z, then we miss the point of the order model. So we have to include all the effects together. And then what we are doing in our work is break up this domain into tiny chunks of vortex patches and put a point vortex in each of those chunks. And I think if you look at the printout, it is clear because you see those black dots. Those are the locations of the point vortices, and we are trying to develop the reduced order model accordingly. That is a different discussion. What I'm trying to focus on is, or basically highlight is, the secondary flow features can have a distinct impact on the eventual particle transport that we are doing today. So let me write down some comments over here. So just to clarify, this is X vorticity, this is Y vorticity, and this is Z vorticity. I have already included the coordinate directions over here, so X is into the plane. And this is the vorticity magnitude. So in the upper airway, upper airway owing to the large Reynolds number. The convective term is dominant. And we have already discussed about certain points that I have over here. Let's quickly jump into what is the source of this vortex formations. So this is happening as a result of both the shearing action and the centrifugal force of the flow. So there is an imbalance, and that imbalance creates this strong vortex patches. Let me write down this statement first. So as the fluid particle moves around the around a bend, as I said, even in the nasal space there could be some vortex formations because there are also some topological deformations where the fluid particle might have to navigate a bend. But it becomes more prominent when the airway is most constricted, which is near the larynx. So as the fluid particle moves around a bend of fluctuating curvature, the imbalance between the centrifugal force and the pressure gradient leads to instability, and and the resulting vortex formation. Okay. And yes. Okay. Any questions until now on this? So,
Gravity influence also.
the gravity influence is there, yes. As I think I have, no, this is in my research talk. So the gravity influence could be there. Yes.
What I see in the diagram of gravity is
Yeah, so these simulations we do include the gravity. Is there, right? Yes, yes, we do include the gravity. But the thing is, the gravity effect is more prominent on the particles rather than on the flow. So if you simulate with gravity, without gravity in your flow, you will not see much difference. The particle transport, you will see some difference. Okay, let's close it here.
So we can start at maybe 8:35, 15 minutes from now. We can have the source which I already there and let's start. So just as I understood also. Discuss about turbulent flow. Inertial force by the viscous force, and then, like, let's say if we define the inertial force rho L cube, we take the acceleration, the convective term. We can also write the v by t, but that will again we can convert it to the in terms of L by u. So v dv dx, let's say, so we can write u square by L here, and then, or like if you write like this v by t, we can say like u t, we can again write like this, it eventually becomes u square by L. Then viscous force, take the viscosity, the area is L square, and let's say del u del y, you can take as u by L. So then it becomes first, let's say rho L square u square, here also mu into ul. So eventually we achieve the final form which is usually accustomed to. Then it can also be interpreted as like the viscous time scale by the inertial time scale. So from this definition, we can say that when Reynolds number is high, inertial force is much more dominant compared to the viscous force. In this definition, first let's define the viscous time scale is L square by nu. So you can see here it is dimensionally constant, like consistent. This is meter square, let's say, in SI system. Nu is meter square per second. So ultimately L square by nu term will give a unit of second. The integral time scale, inertial time scale, we can say simply as L by U. So thereby we can rearrange as UL by mu. So we can say that when Reynolds number is very high, the viscous time scale is much higher compared to the inertial time scale. So this, like one can be interpreted in terms of force, one can be interpreted in terms of the two time scales. So in context of, just like since I am like also teaching the convective heat transfer, there is a non-dimensional quantity called Beckley number, which we generally say like the diffuser time scale by the inertial time scale. So when it is like thermal diffusion, we write as L square by alpha. Alpha is the thermal diffusivity, and inertial time scale is the typical L by T. So this eventually becomes UL by alpha. In the chemical engineering context, many times this alpha, instead of the thermal diffusion coefficient, we go by the mass diffusion D. So then it becomes UD by, sorry, this is UL by D, more like a diffusion coefficient. So these are the the two time scale definition. So let's say that like when we like focus on the audio is okay. So when we refer to the turbulent flow, first we say that like the Reynolds number is obviously very high, so quite high. Then generally we say that the flow is chaotic. Again, like the chaotic aspect requires much more discussion. We are skipping for the time being. What we say that like let's say in a turbulent flow, if there is slight variation in the initial conditions, it will lead to different trajectories. Like let's say here we take at a single point, there are certain variations in the initial conditions. One flow trajectory will be like this, another trajectory may be like initially close to each other, but it will land at some other place. Okay. Then we say, like always we say that if we look at the velocity, it is always a fluctuating or like random and fluctuating. So, like let's say Reynolds studied everything qualitatively. Later, with hot wire anemometry, or like much later when people studied like PIV, they saw like let's say like with a device which measures signal in the laminar flow, it looks like a straight line. The velocity signal, okay, or like very small, like these sort of small oscillations. These fluctuating components are in the range of the least count of the instrument. Okay, very like smooth signal. Whereas, like let's say at a single location, if the flow is turbulent, the velocity is like quite. We have a mean component, but it is fluctuating about the mean component. So if we look at the absolute magnitude of the velocity for like let's say at a given Reynolds number, let's say in a pipe flow Reynolds number around 10,000. Okay. So then like in each different measurement, here is one signal, the other signal will not exactly match with each other. So it will what you have like some sort of other kind of signal will come. So each measurement will produce unique sort of velocity. But like what Reynolds proposed, that in this kind of scenario, since we are not like getting, like we can't predict the exact this kind of behavior, what we should do, we should focus on the mean quantity and then like subtract the mean quantity from the actual quantity. So let's say if at a given location we can like decompose this as the mean component and the fluctuating component. So this is mean component U bar and U dash is the fluctuating. And then he says that like let's say at the Reynolds number 10 to the power 4, even if the two velocity signals are not matching with each other, it is highly likely that the mean component will be same. And also, if we take a statistics of the fluctuating component, that will be similar to each other. Although the individual components may not be overlapping with each other. So, let's say, how do we do the mean? One is like the time averaging. So, at a given location, let's say u bar x or x0, x0 implies the three coordinates. You can say, let's say, if we measure the velocity for a given amount of time, capital T, if we starting from T1 to T2, whereas T2 minus T1 equal to T, and let's say the U is measured at this location and for time T dt. So this is the time averaging procedure. So in this context, just a funny story, in the IT Roper faculty interview, someone asked what do you mean by the time averaging of this quantity. So I simply wrote from 0 to T or 0 to capital T 1 by T ux0 comma T dt. So one professor was not happy with the definition. He didn't like the idea of assigning the lower integration limit to 0. He said that let's not keep it 0, rather write T1 and T2. So it's a matter of definition. Just if we write from T1 to T2, just remember that the difference of the two times is the capital T. Okay? Or otherwise we can start from 0, write capital T here, and then we divide by the capital T. So, you can see that this is u equal to u bar plus u dash. If we take the mean of the two quantities, both the sides, taking mean of both sides, what we do? Let's say this over bar represents taking mean. So u bar plus u dash, we write like this. Then this quantity is already mean. So definitely taking mean of a constant quantity will give the same term. So u bar plus u dash bar. Now you can see these two terms are equal to each other. So essentially, by definition, the mean of the fluctuating quantity, that will be 0. So this property will be always used while we derive the Grant's equations. So let me just write here one part. So any fluctuating quantity, let's say u dash or p dash w dash, the mean of this fluctuating quantity, or let's say for the pressure component, if we write the fluctuating pressure, by definition, the mean of these fluctuating components are 0. So then, just like time averaging, there are two other types of averaging. Let's say at a single time we are measuring over a 2D or 3D field at a single instant. So here u at a given time instant t1, let's say, and the area or the volume whatever we are let's say for the sake of generality we divide by the total volume. Then let's say over the whole field. So you can write the three coordinates and at a single time instant into let's say dx dy dz. So basically let's say for the sake of simplicity we take a 2D planar field, we measure at 10 different locations at a single time instant, and then we take the average of these 10 points, and then we say that what is the space average quantity. So that space average basically gives an idea that whether the velocity is homogeneous, or what is the the degree of variation in the whole flow field. That sort of space ability. Then the ensemble averaging. So that basically, let's say we have a very easy experiment to do. We carry out the, let's say, some pipe flow experiment. I equal to 10 to the power 4 just for example here, and then over the cross section we are doing some sort of PIV measurement, and we are carrying it out 10 times, or some other easy experiments we are carrying it out 100 times. So then, like for the single location we are having 100 measurements, and then we do the averaging procedure. That will be the ensemble averaging. For our RANS derivations, we will be sticking to the time average the time average method. And also one thing, so these are the for the RANS simulation, we will be sticking to the time averaging procedure. Right. So RANS is Reynolds averaged Navier-Stokes equation. So I will just writing down the first two ones. The Navier-Stokes is obvious. So Reynolds average. Okay. So here one thing, there is some term called stationary turbulence. By stationary turbulence means, let's say we take this mean component. When it is stationary turbulence, the mean quantity is not changing over time. So let's say some sort of signal is like this. If we take the mean of this quantity, so let's say this is U versus T, then the mean quantity is not changing. But let's say some sort of pulsatile flow or some whatever, some time average, but the mean component is changing. So let's say some sort of the mean is changing like this, and the velocity signal is some sort of fluctuating about this mean quantity. So here it is clear that when you are calculating U versus T and plotting, if we plot the mean quantity, this curved line represents the mean component. Okay. So in this case, the mean component is changing. So then, let's say for the stationary turbulence, when we are writing the time derivative term, if we assume the stationary turbulence, this we can take as 0. But for non-stationary one, since this mean quantity is changing, stationary turbulence where the mean component is also fluctuating, we can we have to consider the time derivative term. Okay. Okay, so we said initially that any quantity you can write like U bar plus U dash, same goes with the other quantities. So let's start with the continuity equation. You know that here again we are using incompressible flow. So for incompressible flow, we can simply take the divergence of the velocity field is equal to 0. So let's say divergence of velocity field is equal to 0. Following that, if we write down the index notation like del u I del xi or del u j del x equal to 0. Following that, let's write down first del u del x. We will just using two components, but you keep in mind that in general it is three components, del u x, del u y equal to 0. Now, let's say we are assuming turbulent flow. So essentially, we can write like this: u bar plus u dash plus del del y v bar plus v dash equal to 0. Again, if we carry out the averaging procedure, let's say we carry out the averaging procedure here, the next step it will come del del x u bar plus del del y v bar equal to 0. So this shows that the mean components are following 2. Then if we just simply subtract the equation 2 from the general equation 1, we can also show that del u dash del x plus del b dash del y is equal to 0. So this shows that, so this equation 3 is essentially, here you can see that we are starting with the general continuity equation for 2D flows. Then we are doing the averaging procedure. We are showing that the mean components are following the continuity equation, and after that we subtract the mean equation from the first one, and we are showing that the fluctuating components are also following the continuity equation. Okay. So this part I keep it intact. We can write the momentum equation in the other half. So we start with the x equation, like the, let's say the x momentum equation. We'll start with the, like this, rho del u del t plus del del x u square. You can write u dot grad u, but I will just carry out the averaging procedure. For this purpose, I am writing like this: del del y u v plus del del z u w. So this is the LHS part, the left hand side part. Then we can write equal to minus del v del x, and plus we already know that mu of Laplacian square u, but then again, like, we will write this term now in terms of the shear stress. So let's say for the, let's just recalculate the stress tensor. You can hear, right? आपको सुनाई दे रहा है? Okay. So let's say tau xx, tau xy, tau xz. We follow this column only, tau yx now, tau zx. So if you remember the stress tensor, we know that along this column, like let's say tau ij, when I am saying in terms of the index notation, I is the area vector direction, right? And j is the actually the stress direction. So let's say if the area vector in this case is acting in the positive x direction, so here, like let's say sigma xx represents that the area vector is in the x direction, and it is also as well acting in the x direction here. Now let's say this is x, this is y, and this is z. So you can see vertically the stress component, its area vector, if we write like tau, the area vector will be, the first index will be always x, right? And since it is acting in the z direction, you can write like tau xz. Following that, like perpendicular to the board, this is or rather if we like draw like this will be tau yz. On the other hand, so basically the row wise component represents the stress having all the area vectors common, right? That is in the x direction. While sorry, this should be tau xy, right? So x is the area vector and y is the direction. So the column wise stress components basically represents the stress components acting in the x direction. But please note the fast index are different for the cases. For the x momentum, it will be the first column, that is tau xx, tau yx. Basically, this area vector is acting in the y direction, but this component is acting in the x direction. Okay, so let's just see here. You can write this as the right hand side term equal to minus del T del x. Again, here we are intentionally dropping the body force term because body force will be not fluctuating. So that is the assumption. So you can write del x tau xx plus del y tau yx plus del z tau zx. Okay. Here you can see that if we carry out the averaging procedure, the del p del x term you can write, you can see from that side this board, right? It's not a problem. So at least the del p del x, if we carry out the averaging term, that is the easiest one. So p is p bar plus p dash. So when you are writing like this, so essentially if we write like this, it becomes only del p bar del x. This term, the del x of p dash, this is 0, so this is dropping out. Similarly, here the viscous terms mu grad square u, if we carry out the averaging procedure, this becomes mu grad square u bar only. The fluctuating component dies out. So the stress components again, like this, when you carry out the averaging procedure, we simply write like this, tau xx bar. Okay. So this means, like let's say tau xx, if we write the general term, here p is already exclusively written. So minus p plus let's say 2 mu del u del x. Okay. So when we carry out the, let's say for the time being, since we have already exclusively written the p term, if we carry out the averaging procedure, this becomes 2 mu del u bar del x. Okay. So then, like when we are carrying out the right hand side term averaging, here we are writing equal to minus del t bar del x plus del x. So this now just involves the derivative terms involving the mean velocity component plus the del y tau yx bar plus del z tau zx bar. So just for the, like if you recall here, you can write down the index term and you can also expand the, so let's say tau ij equal to minus p delta ij plus 2 mu Sij. Sij is the velocity gradient terms. So Sij. So please note here, I haven't like wrote the lambda term because we are assuming that it is incompressible. So this is half del ui del xj plus del uj del xi. So when we are writing the tau xy term, this is Kronecker delta. This anyway will cancel out. So you can write 2 mu half of, like let's say x is 1 and y is 2. So you can write del u by del y, right, plus del v by del x. So this becomes mu del u del y plus del v del x term. Similarly, if you expand the tau zx term, this will be tau zx term equal to mu del u del z plus del w by del x. Later if we simplify, you can see that some of the terms will cancel out by using the divergence of velocity term equal to 0, and essentially when we expand on the terms, we will be getting the Laplacian of mu grad square u. Okay. Similarly, when in the y direction momentum equation, we will be landing up with the Laplacian of mu, like mu Laplacian of v and mu Laplacian of w. So here, so let me just write down maybe the y momentum equation. We know that there will be mu grad square v and mu grad square w, but this essentially comes from this sort of derivatives. So here, let me just write it anyway. First, here you can see that tau xy, this will be like tau yy and tau z1. So in the y direction, it will be del x tau xy plus del y tau yy plus del z tau z. So here also you can see that if you note the second index, all are y, but the first index, they are acting in, the area vectors are acting in the different directions, that is x, y and z. Similarly, in the z axis, you can see the component, the second index will be always same, tau xz, this one will be tau yz, and this one will be tau zz. So if we like follow this pattern, we can write this is varying along the x, this is varying along y, and this is varying along z. So again, the right hand side stress components for the z direction, the simplified term we have already written mu, that's Laplacian of w, but when we write down like this del x, this will be del x of tau xz plus del y of tau yz plus the del z term of tau zz. Okay. So in this way, like when we do the actual derivation starting from, let's say, simple like this sort of cubic fluid element, we take into account the stress components in this way. First we write down the derivatives of the stress components, and then we, like for incompressible flow, we simplify to the Laplacian of the individual u or v or w. So let's write down first here. Let me just write down the x equation. So let me just write down in a single row. W equal to minus del x plus del x term, which is tau xx plus del y tau yx plus del z tau zx. And here, if we assume here the stationary turbulence, when we carry out the averaging procedure, that will be 0. If we don't want to neglect this term, we assume, like for a general case, we can write here this term. After averaging, you can write dV by dt. So just keep in mind the certain definition of the stationary turbulence concept. Means ideally, like turbulence is always fluctuating. This stationary turbulence, it deals with the mean component. Okay. So now we will just take account of the one of these convective terms. So let's say u square. This becomes u bar plus u dash and u bar plus u dash. We write down this term also. This is u bar plus u dash, v bar plus v dash. So you can see we just simply write down u bar square plus u bar u dash. This we multiply now. Let's write down like this: u dash by u dash into u bar plus u dash square. Now we do the averaging procedure. Let's write down like this. First, carry out the mean of all these quantities. Following that, this is a constant quantity. This will be as it is. Now, the u bar, u dash part, when we carry out like this becomes like this into u dash. And by definition, we know the mean of this fluctuating quantity is 0. So this becomes 0 here. So you can see here that this term and this term are essentially same. So both these quantities are 0 plus 0 plus 0. But we have said that mean of the fluctuating component is 0. But this is a positive quantity, right? The mean may be, let's say, like if this is the mean component u bar, in this part it has the fluctuating component u dash, it will be negative, here it is positive. But when you are carrying out the square term, it is always giving a positive quantity, and this is always in non-zero form. Okay. So u bar square plus u dash square. Likewise, if we carry out the averaging procedure of this one, you can write here that u dash v dash, or we can write it together also. This implies that uv mean of the product of the mean of the product of the mean components uv, or rather write like this to avoid any confusion. U dash v dash is like a non-zero quantity. So this has been, here it is easy to prove the u dash square or v dash square or w dash square, this will be always non-zero. What about the mean of the two different components? So this is like little bit some sort of, we take a simplistic scenario and we show, later we will just show that it is always like a positive quantity when we will define the Reynolds stress term. For the time being, just think that product of this product of these fluctuating components are non-zero. We can't rule out them. So u dash v dash. Likewise, the third term will also be the u plus u bar plus u dash, w bar plus w dash. When you carry out the averaging procedure, this will become u bar w bar plus u dash w dash mean. Okay. So one point, like when the mean component is multiplied with the fluctuating component, and then we take it, then we are taking the averaging procedure, this will become 0. But when the individual fluctuating components are multiplied with each other, then when we are taking the mean, it is a non-zero quantity. So therefore, you can see u dash square, mean of the u dash square, mean of u dash v dash, and mean of u dash w dash, those will come into picture. So let's write down the left hand side average quantities here. So this term will give these two terms. One is the square of the mean component, and one is the mean of the squared fluctuating component. Likewise here, del y, this becomes u write like this, del z, sorry, del y, u dash v dash here, and this one is del z, u w, or w like this in this way, u dash w dash. And these ones like minus del p bar del x plus, I am not writing the three components, just writing one component. The two components will be written like same way, del x tau xx in this way, right? The other two components also will write in this. Okay, so now you have seen that these three terms are generating six components. Huh?
First, the U bar, U bar, because we replace the U bar as well.
Which one you can come by this time?
Like in the first time, U is always replaced by U bar as we are going to just check that in because we replace the U bar plus.
Oh, acha. So let's, for the sake of, we make it stationary turbulence. The confusion now. Okay, let's remove it. So here, like we are assuming stationary turbulence, so that's why we are dropping the term, and then we are just left with the three terms, and these three terms, after erasing, are generating the six terms. So what we do are seeing now, like normally these components are taken in this part, and they are said that these are Reynolds stress terms. But actually, if you see the derivation, these terms are arising. So essentially, how are these terms coming? This, when we are like doing the momentum equation derivation, this is basically the variation of the momentum flux in the different directions, right? So you can imagine that this is the variation of the momentum flux due to the mean component, and this is the variation of the momentum flux due to the fluctuating component. Although normally, like in the when we like don't look at the derivation part, we straight away say that these components will come into this side, and we term those as Reynolds stress. Okay, but the physical significance is, please remember, is not stress actually, is arising due to the whole fluctuating component. Later we will club together in terms of the stress component. So here, like after this, let's write down, like we are dropping the stationary term. So on this side, if we write the derivative term, we can also drop as like depending upon the choice. I will just keep it because I like later want to show that it can be clubbed together. So let's say we are writing like this: del x u bar square plus del y u bar v bar plus del z u bar w dash. And on the other side, we are writing minus del v bar del x plus del x tau xx minus, so you can see we'll take this component, sorry here, is there any color chalk, then it will be easier. आप कोई कलर चौक दिख रहा है? सभी पॉइंट okay, so here you can see that these are the fluctuating components. This again, this is one and this is one. So these will take on the other side. Now we are writing like this: minus rho u dash square plus del y tau yx minus rho u dash v dash plus del z tau Zx minus rho u dash w dash. Okay, so now you can see after the emerging procedure, we are taking the fluctuating components in the this side and we are clubbing it with this one. Okay, so please see, this is again over bar. So tau over bar xx essentially means 2 mu del u bar del x. Tau yx means del u bar del y plus del v bar del x. So even if I forget to remember, like write the over bar symbol, please assume that this is Everest quantity. Okay. So how much time? I guess I have still less time, some 15 minutes time. So now you can see that this one and eventually these four terms, let's just write here del bar del t here. So this can be further simplified as del bar del t. The left hand side terms, if you carry out the averaging procedure and following using the impermissible flow conditions, you can finally write the left hand side as like this one. Okay. The pressure components will be always minus del p bar del x minus del p bar del y minus del p bar del z. If we consider the body force, we are saying that the body force is not fluctuating. So, for the sake of convenience, we are just dropping those terms. And even if there is any body force term, that will be not like having any mean or fluctuating component. The gravitational force will be always as it is, or electromagnetic force will never fluctuate. And even if it fluctuates, like Coulomb is doing some electromagnetic force, that is not like this typical turbulent fluctuating quantities. Okay, so these are the, this one is essentially the left hand side, this is the pressure gradient term. If we now look at the stress components, so let's just write down the stress component here. We just derive the left hand side, sorry, the x momentum equation. The stress component will be tau xx minus rho u dash square plus del y tau yx bar minus rho u dash v dash plus del z tau zx minus rho u dash w dash. So now you can see here that is u dash square, u dash v dash and u dash w dash. If we club all the three like directions, first write down. So this is the x momentum tau zy. It is varying along x, it is varying along y, and it is varying along z. So when we carry out the averaging procedure here, we are writing del x tau xy minus here now it will be, or let me just write down the Reynolds stress in matrix form first, that will be easier. So normally we write, let's say, rho ui dash uj dash. We expand this in the matrix form, like let's say minus of rho. This will be u dash square. This will be u dash v dash. This will be u dash w dash. Okay. Now here this component will be u dash v dash. This will be v dash square and this will be v dash w dash. and here it is u dash w dash, it is v dash w dash here, and w dash square. So, one thing you can see that if we follow the actual stress component convention, we can say that when we are using the x momentum, this column is used. When we are using the second one, y, the second column will be used. So then you can see if you follow the Reynolds stress matrix, the second component, if we look here, you can write here u dash v dash. Then del y, this is bar again. We know this will be yy minus the rho, which component? This component should come, right? V dash square. So here rho v dash square term is coming, plus the del z tau zy bar minus rho w dash square. Now follow this logic and try to derive the z momentum equation and tell me, or one of you can come and write down. So see, look.
That one is rho v dash w dash.
Rho, sorry. So this should be rho w dash v dash, right? So maybe it's okay, right?
Yeah.
Huh?
For the vice versa.
So no, for the z momentum. So z momentum involves, let me just write down the stress components for you. So this will be tau xz, tau yz, and tau zz. Okay. And these are the Reynolds stress components in the z direction. So Sasikant will try to just write down the stress components in the z direction following this logic. U dash W dash. Okay. So this is correct, right? What is he has written. So you get the logic. Like initially, instead of writing the mu Laplacian of u, we have written the direct stress component so that we can just club these quantities together with the x terms. And that's kind of like after doing this algebraic operation, since it is clubbed with the stress component, that's why we call it Reynolds stress. Although we just said that physically it implies the momentum flux due to the fluctuating components. So please keep in mind about the physical significance. Okay, so now if you look here, this is the matrix here. So you can see that these two are equivalent, these two are equivalent, these two are equivalent. So here it's a symmetric one, right? So this is symmetric and 6 unique or individual components have come. So earlier, like let's say for a simple laminar case, we are using the 3 momentum equations and the continuity equation. So u, v, w and p, these are the unknown terms. We can find out from 4 different equations, 4 different variables. Here we are using the 4 different equations, the continuity equation and the 3 average momentum equation. But then we have no clue about these 6 individual components. The averaging procedure is generating 6 unique components. So that's why like the number of variables are more than the governing equations. So that is like, let's say, since we do not know anything about these average quantities, if we further carry out the averaging procedure, in the next step what you will see like some sort of rho ddt, like let's say ui uj dash average quantity, this will be generating some equation which will be ui uj uk dash. So this will be now triple product of three fluctuating components. This again it will be three like more number of equations. So like if we further carry out this one, this will involve some equation which will generate ui dash j dash k dash and u k dash. So it's a never-ending problem, right? So this problem in turbulence is called the turbulence closure problem. So that is why, like, we do some approximations. So there is not too much time. I just want to stop here, and we'll like continue this part in the next class later. We'll like discuss the schedule later. And so that's all for now. We carried out the averaging procedure, and then we showed that these are actually not stress components. And due to the averaging procedure, analytically if we try to solve, this will not be like this will not make our life easier, and that's why since the number of variables are will always be more than the number of governing equations, we say it is a turbulence closure problem. Later, how to deal with turbulence closure problem in the next session we discuss that. Okay. So let's go to the mechanical seminar, and we'll start at 12. And the
And in terms of the dimension, this is a mean number, of course, 5 and 10 micron. In certain regions, that here there could be bigger. So the overall thickness of this could be around 50 microns. So, and the ciliary motion goes on here. That helps to slowly move this thing around. And ciliary dynamics is another entirely different subarea of fluid mechanics as we know. So we are not going to get into any of this, but I still wanted to show you what the general profile is like for the mucociliary surface. Now, in our work, since we model the airflow and then particle transport, as I think I have already mentioned, and I definitely did mention during the talk, that the timescale of this mucus motion is much longer than the timescale of the airflow brushing past it. So we don't really need to think about the wall to be a moving wall. We can still think that the wall is static, and that's what we use in the simulations and for that matter in any kind of modeling. But what is interesting is where that particle has landed. So we know that if you remember some of the aspects that I covered during the talk, the targeted deposition at the downwind sites like the lithophytes is quite low. It's typically always below 10%. There could be some exceptions, but yeah, sub 10%. So most of the particles are landing. So if this is the airway, so most of these particles are landing in this region, in the anterior part of the airway. So once they have deposited on the mucus, they are moving with the mucus further downstream. And the target site, let's assume that this is the target site where we have to send, if it's a drug delivery application, that's where we have to send the drug subject. So now, if you think about what is going on the surface here. So I'm looking at the surface from the side. So this is the epithelial tissue. Let's assume that this entire region is this mucus layer with the cilia over here. At the anterior part, the droplet has landed, or the aerosol has landed. It has some solutes in there, and now it has started to move with the mucociliary stream, right? While it does that, these solutes are getting over that mucus film, and probably they're penetrating through the gel layer as well. So there is a time scale for that penetration, there is a time scale for the downstream transport. So if the target site where we have to send that drug is, let's imagine that it's here, by the time this drop ends up here and these solutes have managed to percolate, if that matches, then we have targeted drug delivery even without directly depositing those droplets at the target site. So that is one thing. Also, the other open question is, if I do manage to directly land the droplet over here, is it sufficient, or are the particulates not going to penetrate through the gel layer of the mucus to the target site, and are we missing the point altogether? These are open questions. There is no work yet on all these things, but something to think about. In terms of the state of art, what people do, they do not think, they think that this is the best possible option to land directly at the target site, fine. But for the anterior deposited droplets, what they do is, they don't think too much about the penetration through the mucus. What they track is, they unwrap this 3D surface into a 2D domain. So it would look something like this once you unwrap. So basically you're opening up that 3D enclosure onto a 2D plane. So these particulates, they have landed over here, and the mucus is moving like this on the surface, being generated from the goblet cells, and then they track where these particles are going to move with the mucus. So it's a surface, a 2D model, an unwrapped 2D model. So that's what the state of art is. So as you can guess, there are a lot of things that can be done with this. And the good part is, the cilia hydrodynamics is a very mature field in fluid mechanics. So there's a lot of work that has been done. One of our common friends, for example, Levan Groto, has done a lot of work on ciliary hydrodynamics. So it is important for us to connect with that community to figure out whether we can use some of their results and put that into this physiologically realistic models. That has not happened yet, truly. Like, they have worked on some non-human animals, but not so much in the human systems. Not in a physiologically realistic way. They have idealized the systems a little bit too much as of now. So, like the way we are now applying CMT realistically in the human systems, I think it is time that we talk with them, collaborate with them to make sure that it is included.
Like cilia sizes are of what? Micron size?
If the periciliary layer is 5 micron, the length, max around that. And then the thickness is very finer.
And motion is also around microns per second or something.
I don't know. I have to look up.
The drop which we are making, we are talking about the diffusion of particles in this state.
Yeah.
That is not the real
No. What I drew over here is no one has worked on that yet. So it is something that to explore. Because think about the nanosolid mechanodynamics through these gel layers. It is a complex enough. It is a non-Newtonian liquid. So it is not trivial, any of that. Yeah. So if any of you get interested in pursuing research on this topic, there is like 20 years worth of things that can be done for the next generation. So I included this picture into the lecture notes. Let me write down some comments before I move to the idealized profit problem. So The air is brushing past this gel layer at the top. So this is interaction. Well, the name of the topic that I've given here is interaction between air and mucus film. I have so the paper that you read on the first day with from Sani Jan. So with him, we have some collaborations as well to look at drop impact. So what Sani does is basically use glycerol as stand-in. There is a lot of things that can be done. Okay, so let me write down some comments here. So we have been discussing only about the fluidic motion of air and the flow induced particles within the respiratory tract. But if you do work like this, and if you show it to your community, they will ask, as I was asked during the talk, after the talk, that what about the mucus? So that is a very valid question that you always would get asked. So, however, we do need to remember that the airways are lined with a liquid mucus layer. Now, that statement itself is quite intriguing because yes, we do know that there is a mucus layer, but do you really know how the thickness varies throughout the domain? We probably don't. We don't, and that is crucial because what I had assumed in my infection transmission model was this, and that was dictated by that cell paper that came out from UNC that yes, the ciliated epithelial cells with the ACE2 surface receptor that the virus will bind to is there throughout the entire airway. Why did we assume that nasopharynx is the first hotspot? Because the mucus layer is thinner at the nasopharynx compared to the outer parts of the nose. But did we think a lot about the thickness profile? We did not. We just assumed that it is thinner, and hence, if some droplet directly ends up over there, they would be effective enough at intruding into those cells. So there is some leap of faith going on over here, if you can read between the lines. And there is work that needs to be done in those areas. Well,
So no one really knows the fitness profile like along the pathways.
most
Just
of
assume that 5
like the in vivo data is rare to come by. Like they do a lot of cell culture studies, but that is not in vivo data. And also like how the thickness profile varies between healthy and someone who already has some kind of infection. Okay, so this layer is, let me keep on writing. So this layer is relatively thin. On the scale of tens of microns. And is usually expected to have little impact on the air mechanics. So that is fine. So we know that for sure that the timescales don't match, so we don't have to worry about that wall effect, moving wall boundary effect on the air flux. But the fact that we are assuming that something depositing directly over there is potent enough for whether it is for drug delivery or it's for targeted infection. That if you ever write a paper on that, and if you read my papers, I add that as a caveat, as a discussion item. So it is important as mechanicians to understand what are the current limitations in our work. Because most of us here are students, there is this, many young scientists, they think that what they're doing is end all and be all, but that is not the case. We all have limitations in our work, and it is important to break through those limitations. Okay, so it would have little impact on the air mechanics, the reason being the time scale. Of mucociliary downstream transport is being much, much longer than the inhaled and, for that matter, exhaled air's motions timescale. Okay. But to this point, I don't have this cartoon on the lecture notes. But let me comment on this as well. So, however, mucociliary movement in many textbooks or papers, they would call it as mucociliary clearance as well. So mucociliary clearance could be critical for targeted delivery of pharmaceutical solutes that have landed along the anterior parts of the airway. That's a drug delivery application, but the same is true for pathogen embedded particles as well. And maybe at some point I'll get some time to explore this as well. Another thing that's something to think about for us mechanicians is where this mucus is getting secreted from. So that is something that we, Dr. Shamanta and I have discussed as well while trying to develop realistic models. That is something that we need to know from the biologists, that where the source is, because as field mechanicians we know that whatever model we might have, when the source is important, we know for the airflow, of course the source is at the inlet, that's fine. But if it is a biological fluid which is getting secreted, it is not so obvious. And that is something that we have to fight with as well. Anyways, okay, any questions on this? If you get any new ideas on how to approach things like this, you don't have to tell me right now, but I'd be happy to discuss, because these are primarily uncharted waters for most of us.
One comment may be like basically motions are oscillating.
Yes.
These will be mostly, I guess, in the creeping flow region, or somewhere very low.
Yeah.
On the other hand, there people are like simulating flow over a canopy or like flow over planktons in the seas. Those are again like large scale erosion. Although like they move, I guess they do the oscillation thing, but the erosion regimes are completely different. So this just reminds me about the flow over planktons or flow over the.
So, what did I look at? So, did you read this paper by James Blake from the 70s? So, when I was.
You can write down the name, you can read this.
Yeah, so. James Blake. So, he wrote a very thought-provoking. It was primarily given as a lecture, which was then written verbatim as a paper. So, there he posed many open problems. One of them was if you think about a torus, and you have cilia on top of the torus, on the surface of the torus, and the cilia is beating like this, it can self-propel itself in a Stokes flow. So in a Stokes flow, as we know that motion is reversible. So it is like if you swing in the backstroke, you would go back, so you cannot move forward. So every motion is reversible. But with that kind of ciliary motion, even at
James
low.
Blake or 8%?
8% was another.
Because there is something called Scallops theorem.
The scallop theorem is by Purcell, but I believe it is James Blake. But Purcell's work is also relevant here. Yeah, that is called the scallop theorem, right? That motion thing. So the torus problem was unsolved, and this is I'm talking about 2007 when I was an undergraduate. So I got this JNCSR fellowship, and I worked at IMSC, and that was the problem that I worked on. I could not solve it. Someone else published it after a few years, but yes. Speaking of that, yes, it's a Stokes flow. It's a creeping flow. That's what that application was as well. So that would be a standard approach. Now, whether we can, and I think many of the ciliary hydrodynamics community members, they are using those tools. What they are still not using is, when I go to the DFT, they are using geometries that are idealized, flat plane, spherical. They are not used to using topology that varies regularly. So the geometry equations, they cannot be the ones that they're using.
And company doing part of this bacterial motion.
Yeah.
He studied also some South Korean guy, Park or something.
Yeah. Onshun Park. Onshun Park is at Santa Clara. So something to think about how to adopt those tools, and it's a very rich source of tools that they have developed over the last 20-30 years. How we can bring them into real biohydrodynamics. Okay, so let's move on. And this topic that I'm starting now, and so what is the timeline that we are going to follow? We are going till 4:30 and then?
Yeah, we'll go till 4:30, then 15 minutes break, 4:45 to 5:45 or whatever you feel like.
Yeah.
You can stop at 5:30 also.
Okay, so I will lead beyond 4:30. So we'll have another session as well, of course. So this topic would be for the idealized flow field. I'm going to develop the theoretical formulation, which I think you have seen before as well, hopefully. But then try to solve a problem on that and see what the comparison would be with a full-scale CFD versus this analytical result. So this is. Okay, I don't think I have this printout, so let's use this. So this is the idealized modeling of inner airflow, and this is what I'm measuring. So like a pipe system that we use to study particle transport, we are getting inspired by simplification. So this is a curved symmetrical geometry. The flow is driven by that pressure gradient delta P, P1 minus P2. I don't have this as printout, right? Could you just check in your set? This diagram? No. Once you are done. So this is a curved section. The flow is moving UZ, and the coordinates would be R theta Z. So let me draw it out on the screen. So idealized modeling of inhaled airflow. So we have a system like this. The flow would be under the delta P, P1 minus P2, where P1 is on this cross section and P2 is over here, so P1 is greater than P2. The flow velocity is in the z direction, uz, and we are going to use the r theta z system. So this, the central axis, which is not a straight line, which is a curved path, is the z direction, the radial direction. And then if I look at any random cross section on this, so it's a circular cylinder, so we have a circle where the radial direction is like this and theta is measured in this way. So with r theta z, these three coordinates, we should be able to know what is the location of any fluid molecule over here. So theta. And z is, if I look at it like this, z is out of the plane. The other assumptions that I'm going to impose is, this is a constant cross section, so if the radius is, let's assume it to be r, it is going to stay constant. When we do the corresponding integrations, we can directly use that value as a constant. So this is the setup that I'm assuming. Let's see what the equations could be. In terms of the constraints in the flow field as such, we're going to assume that it is axisymmetric and steady and Newtonian. Why do I mention this? Because when I first started to use this approach, I was trying to develop a model for blood flow. And with blood, you have the problem that it is probably not Newtonian in certain scales. So I want to make sure that this is Newtonian in nature and axisymmetric and steady. So with this, so we have a steady unidirectional flow. And let's now invoke the Navier-Stokes equation. Yes.
Are we assuming that the radius of the channel is sufficiently large to have so that we don't need this whole coordinate system?
So again, the radius of curvature is?
It's large enough to detect the radiation because we are using simple coordinate system.
Yes.
But the channel is a curve.
No, I'm not enforcing that. I don't think I'm enforcing that. But the z direction, so you are suggesting that if it is basically just a straight pipe. No. Z can change. So the z direction is the EC is changing. Okay?
So then for the fluid and for the particle coordinate system will be same. Fluid generally we did in everything, right? So we have to fix a particular framework and then analyze.
In the fluid system, there was a different setup. Not like this. It was a pipe, but not like this. So what we had was, we had the theta and the radius. So basically it was a pipe. The theta angle was different, and then we had the radius. There was no z, right? If you remember. And there as well, that if we had taken something in that direction, that would have changed because it was a circular curvature. And it's in here, and the z is changing. Hopefully that would not have that much of a complex impact on the mathematics, but it's not a straight line. Okay. So Navier-Stokes equation, So in the r theta z system, for steady flow, so the dvdt terms are out. So I'm just going to go to the reduced version of this equation, but it is not. It is going to be in the r theta z system. So it is 1 over r del r of r del uz del r plus 1 over r square del 2 uz plus by del theta 2 is equal to 1 over mu del p del z. So if you do the derivation, this is what Navier stokes would be for in the r theta z coordinates with the time derivative being 0. Now over here, let's see what we can enforce based on the assumptions. So in the assumptions, we have assumed that it is axisymmetric. If that is so, this term is 0. The derivative with respect to theta, that is 0. So we are left with 1 over r del r of r del uz del r is 1 over mu del p del c. Right? Let's put r over here on the other side. Okay, now let's integrate. So integrating with respect to r, we have on the left hand side the del r goes out, so r del uz del r is r square over 2 mu del p del z plus some constant, let's call it a. Okay, and let's call this equation as, we have not named any equation today, so let's call it 1a. Now let's isolate this derivative again. So del uz del r is r over 2 mu del p del z plus a over r. Now what I'm trying to get at is basically a formalism for the flux q for this system. So for which we need to first get the velocity, so we have to do one more layer of integration. So integrating with respect to r again, we have uz as, so there is one r here, so r square over 4 mu del p del z. This is 1 over r, so a natural log of r plus some constant of integration p. So let's call this as equation 2. Now we can evaluate the constants a and b with the boundary conditions. So let's do that. So to compute the integration constants, a, b, so the boundary conditions, so we have this as a setup, right? So the boundary conditions, let's figure out what is happening at small r is equal to capital R, so on the walls. So at small r is equal to capital R, we have uz as 0, no slip. So here again, the no slip condition is equivalent to assuming that the mucus is not moving. So let's plug that thing back over here. So in equation 2 from this page, we just put this boundary condition. So it becomes uz is 0, small r is capital R, so capital R square over 4 mu del P del Z plus A log of R plus B. Let's call this equation 3. So we still have those two unknowns intact, A and B. So let's now use the slope of the well-developed, fully developed flow at the center to get one of the constants. So considering a fully developed flow and the resulting slope in the midsection, we have the midsection has smaller 0 because that's how the coordinate system has been set up. So at smaller is equal to 0, we have del uz del z, which is the slope of the velocity at that point, is 0. So this is r, this is the z direction. Now, if the z direction of the unit vectors for z changes, does it matter? It doesn't, because it's a local solution that we are showing, which is true all along the midsection. So this is the only point where the z term comes up, and I don't think it matters. So at r is equal to 0, del u z del z is 0, so we had del u z del z in equation 1b over here. So let's plug that thing in. So therefore, in 1b, we have 0, 0 over 2 mu del p del z plus a over r. Now, people raise some issues with a divided by 0, so let's, instead of doing it this way, let's do it in a slightly different way. So let me, from 1b, so from 1b, we can write r del u z del r is equal to r square over 2 mu del p del z is a. And mathematically there is nothing stopping us from doing that. So from 1b we get this, and then we apply the boundary condition for r is equal to 0. So as a result, left hand side becomes 0. This is 0 over 2 mu del p del z plus a. So a is 0. So if a is 0, then we can directly use equation 3 to evaluate the other constant of integration, which is a. So thus in equation 3, we have 0 times equal to r square over 4 mu del p del z plus 0 for a0 is b, or b is minus r square over 4 mu del p del z. So we can now plug this all back into this UZ formalism that we have developed in equation 2, that value for b. So therefore putting a and b in equation 2, we have uz is minus r square over 4 mu del p del z 1 minus small r square over capital R square. And so once we have the uz is the streamwise velocity, we can now integrate this over that entire cross-sectional area of the cycle to get the flux. So integrating this this over the entire circular cross section, we have the flow rate Q is equal to minus pi R4 over 8 mu, and then the del P del C. I'm not showing the intermediate steps, you can do it on your own. Use that UC formalism to cover that entire area. What is the name of this formula?
This user is for positive.
Poiseuille's law, right? This is not the Hagen-Poiseuille, this is the Poiseuille's law, or sometimes called the Hagen-Poiseuille. Anyway, so this is what people use to model flow. Different, forget about respiratory system. I know of work from my days as a student at Virginia Tech, they were using this to study how mosquitoes draw blood, the motion through that nectar. Question is how true the assumptions are. Drawing blood to that, is it? Can you assume it is Newtonian, for example? So, but anyway, so this is a very widely used formalism, especially because it is easy to understand. For people who are not fluid mechanicians, they apply this thing a lot. And
Washington himself was a thing,
an engineer, right?
some sort of bio-based you can see. Like he was something measuring the blood pressure or some flow rate in the blood channels.
Yeah.
So that's when the history of involvement of fluid mechanics in medical science is much more.
Now for blood pressure measurement, like the RBCs are 8 microns, WBCs are 16
Things
microns.
like this he did.
He could consider that to be a continuum, but at the mosquito nectar level, I wonder how things happen. Okay, now for the problem that we are going to solve in a while, I'm not going to use a del P del Z profile, rather we are going to use the pressure gradient del P and the del Z, where Z is the, going by this particular diagram that I started out with, Z is the total distance that the fluid particle has traveled. So it is a torque path, it is the distance that it has traveled. So that is the delta Z. So delta Z is not really the level difference, which at least my students at SDSU often take. Okay, so where are we in terms of time? Okay, so let's let me write this last thing down as well, although we are not going to need this for the problem that I'm going to solve. So this is the flow rate. The wall shear could be derived as we know, tau del mu del u z del r. So Newtonian, so the mu is just mu over here. Now this del u z del r we have already seen from the derivation what that is. So we can directly apply this equation 1b to write what it is a being 0. So tau omega, tau wall is tau w mu r over 2 mu del p del c. So from equation 1b. Therefore tau w is r over 2 del p del c. So if you think your system is simple enough, you don't want argument for using this. If we convince ourselves that a blood could still be thought of as a continuum, even while the mosquito is drawing it, one argument that works for them is it is a pipe. It is not a respiratory pathway. It does not have those topological deformations. So it's a pipe at a very small scale. And if you come across those systems, yes, why not? You can use this. And our life will be much less complex. Okay, but if we do want to apply this in systems where the geometric complications are there, all lives would become complex because the results would be misleading. So that's what we are able to see in the example. Question?
Yeah, actually, this formula is for taken positive only, so for just valid for a straight line.
Yeah.
The moment we introduce the curvature, I think this dp by dz we were writing as del p by del.
That's a very basic assumption the axisymmetry breaks down, right? So that is the main assumption.
I was just thinking like there should be some R term which takes care of the radius of curvature of the entire system, but that is not.
Because as we go further along Z, the arc changes. So it would be a function of Z. That means that we are not going to get the constants of integration in this kind of format. So it would be a more complex formalism. Something to work, it's worth thinking about.
So
Yes.
what is the length of this one?
Uh,
Like if length is 2 wide, then that curvature can be.
there will be a length given to you in the problem. So the length here is delta Z. So that is the change in Z coordinate along that straight line.
I think we are doing this to the random.
Yeah. Yeah.
And when it is time to do this. Because the moment we are in element level, we have to, I think, take care of that aspect. In the beginning, it is common.
Yeah. So this is just Purcell's law. There was just one Purcell, right? There are many Bernoullis, but just one Purcell.
3-4 quarters.
Yeah. Okay, so the next thing I should introduce just before we are ready to start the simulations. No, actually we would need this for the problem. Sorry. Okay, so the next thing that we are going to do is to solve a problem, but to prepare for that, we are at this point trying to generate the flow fit in an ideal electricity. That's what we're trying to do, right? So we need to know what kind of flux we are going to simulate. Until now, I have just given you the numbers, right? But since we are also going to run some CFD simulations tomorrow, let me point out how we typically figure out what breathing rate to model. For example, whichever subject you are trying to model the airflow for. So this is guidance for respiratory flow targets. So this comes from the different breathing measurements that have happened over the years. And these are empirical formulas. So we have collected, not us, it started even before I started in this field. So people collected breathing data for males, females in different sitting, walking positions, and then tried to get some kind of statistical trend towards whatever the formulations are. On the other hand, there is a wide body of literature if you are interested on mammalian breathing. So mammals of different sizes, it is possible to derive some kind of power law on what their breathing rates are with respect to their overall body mass. And the same could be true for human beings. So that's what their target was, to figure out some kind of a breathing rate formulation which is a function of the body weight of the person. So that's what I'm going to write down next. So the net, as in the flux going in through both the nostrils, which is what we simulate as well. So I don't think anyone asked me yet. It is, we are simulating the air going through both the nose. It's not like one is holding one side of the nose. So the net inhalation airflow rate has been formulated as, I have it as V dot because I was thinking of back when I wrote it, I was thinking of V as the volume equivalent of volume flux. Q is 2.72 W to the power of 0.44 for male subjects, and for females this is 3.78 W to the power of 0.32. So this is data collected when the subjects were sitting with relaxed breathing. And the W is the body weight in kg, and the V dot is the inhalation rate in liters per minute. And this work is from 2009. And Garcia is one of my sort of seniors in the group. I was a postdoc at University of Germany. So he's a faculty at Wisconsin now. Anyway, so he collected all these measurements, and this is the empirical formulation that they could achieve. So from then onwards, whenever we are trying to simulate flows where we have to develop something specific for that person, we would use that. As in, we have the body weight data for that person. Many times nowadays, now that I am
for sample, how many sample size?
like hundreds. Yeah. So statistically, it was, and they have some correction as well. Like this is the simplified version of the formulation. So they have correction on the power, so it is like 0.44 plus minus 0.1 to something like that. But
this very simplistic relation that it is only dependent upon the body weight.
yeah, and that's what people are trying to get right. So if you think about any mammals, rabbits, dogs, pigs, whales, they have this, they call it the allometrically scaled power law. So allometry means related to the body weight in this case. So that was the idea, like can we get that for human beings as well? Now this is relevant in the sense that if we are trying to develop, so if you're writing a paper for a medical journal, for example, as an engineer, you probably have the data for the person's body weight, the person's gender, etc., etc., and then you generate this very specific flow rate. But if you are writing paper for a fluid mechanics journals, they don't really care. Like if you are modeling 22.78 liters per minute, 20 liters per minute is fine enough. So it depends on the kind of work that you do, but I just wanted to share this with you because the next problem that I'm going to solve would use this formulation, and then we are going to see to generate a similar flow rate or to model a similar flow rate in the idealized system, what difficulties we might come across. So let's stop over here and to continue the next session.
You should contact Ramdev and see the what how much
Okay, well, let's start. So, the idea is now to use the Bernoulli formula, the Poiseuille's formulation that we had developed before on this system. Now, what we have here is this is a geometry for which we had already simulated the airflow. And under the simulation, so this was the allometric target, as in, think about the formula that I just shared with you guys. So this was a male subject. So the first one, 2.72 W to the power of 0.44. The body weight of the person is given as 94.5. So if the body weight, so let me write it down, given weight of the adult male is 94.5 kg weight. Can you just do a quick calculation to check how much the Q would be if it is 94.5 is W? Because I want to double check if that was indeed that allometric target and to see if it's that we used. How much? 20.1. 20 point? Yeah, so I'm right. So this is what we had. So we ran the CRT simulation 20 point, targeting the flow at 20.13 liters per minute. What we achieved was slightly different. We achieved around 20 liters per minute, and that 20 liters per minute was developed under a pressure gradient of 7.78 pascals. So that's the CFD difference. A pressure drop of 7.78 pascals led to a flow rate of 20 liters per minute. Now let's see if we do use this theoretical formulation for the same pressure drop, what kind of flow rate could be generated in a geometry like this. And just a slight, it's not a correction, rather a verification that the derivation that we just did, thanks to it, that it is, you can think of it as something as a straight line as well. Either way, the mathematics doesn't really differ at all, because we are eventually going to see the fluid molecule traversing this delta C. That curvature, if you think back on the formulation, that curvature never plays in the derivation. So this is basically equivalent to a straight path. This picture that I have here, I have included that just to show what is the modern system that I am thinking of in the problem, but you can also think of it as a straight linear pipe. Doesn't matter, because we are claiming that this is the delta Z that the fluid will traverse. And this is given to us as 130 mm or 0.13 meters, and that dimension is an approximate of what the dimension was in the real subject from here to here. Okay, so let's look at the other. So this is the figure. This would be clearer in your printout. So this is the CT scan of the same subject. So this is a sample tomography, computer tomography slice. And to extract the airspace or the airway from this scan, again, I think on your printouts you can see that the whiter parts, they are actually the bony structures. The gray parts, they are the tissues, and then the black ones are the air spaces. So you can see that on the very edge, the black of the outside air matches with the black of the respiratory airspace. So that is dependent on the corresponding radio density value for that region in the picture. So the airway radio density range is between negative 300 to negative 1024 Hounsfield units. You can look up what is Hounsfield unit, but basically it is just a ratio of the different optical refractive indices in this kind of systems. Now, negative 300 to negative 1024, that helps in the case of, I think someone was asking yesterday what kind of tool we use to segment and develop this kind of airspace geometries. There are some open source softwares like Slicer 3D which you can use. We typically use something called Mimics. And be it Slicer 3D or Mimics, you can directly input that this is the radio density range that I want to extract. And that would give you the very first iteration of the geometry. That won't be very useful straight go. So basically you need to then go back into each of the scans. So as I said, it's a collection of different slices collected at different penetrative depths through the head. You look at each scan. After that default thresholding of negative 300 to negative 1024, you have to manually correct the pixels. Sometimes you would pick pixels that are not really part of the airspace. Sometimes you would leave out pixels that should be included in the airspace. And you also need to make sure that the transition from slice 1 to slice 2 is smooth enough. So it cannot be like this. So that's all done typically in collaboration with the doctors, and that's what was done for this person as well. And for that matter, when we get overtly excited, we don't only take the airspace. So over here, we also use the radio density values for the face to generate the face of the person. We just need to make sure that the eyes are closed to make sure that it is de-identified. And you cannot recognize the person from this. Okay, so this is the radio density range value, negative 300 to 801024. The software just for record keeping for this course was Mimics that was used to get this 3D models. So to segment the scans. Okay. Now from here we are trying to get or basically apply what we might get from the reduced from the theoretical model and see how different the values could be compared to the full-scale CFD results that we have already over here. So this is the reduced model for theoretical analysis. Now over here, the mean size, let's assume it to be 1 centimeters, and we are moving from A to B. Assume the delta P A to B to be same as the pressure that could achieve the target 20 liters per minute airflow in the 3D CFD case. So we are going to apply a pressure drop of negative 7.78 pascals. We have already verified that was the first question. If you look at your lecture notes, I first have the students verify the 20.13 liters per minute, the allometric breathing rate. So that was the first question. So in terms of questions, verify the allometric target for the breathing rate. Which we already did. The second question is compare the inhalation airflow rates using theoretical formulation and the given numerical results. And the third part on the lecture notes that we have is explain the difference. And by now we know why there should be differences. the pipe streamline flow is missing all the details of the flow features that are formed in the form of the secondary flow patterns. But let's basically do part B, which is figure out the inhalation flow rate for the idealized model. So part B, delta P is negative 7.78 pascals. And we are trying to generate Q, which is minus pi R4 over 8 mu delta P delta Z. All these parameters are given to us. So minus pi, the radius is 0.01 meters. So 0.01 to the power of 4 by 8. The mu is not given to us, so let's write it down. So mu, we can use the same value that we have been using, but what I have on the lecture notes is 1.825 times 10 to the power of minus 5 Newton second per meter square. And
R is 0.005.
yeah, sorry, yeah, that is right. Now this mu air, by the way, is the viscosity coefficient for inhaled warmed up air. So if you typically look up on the internet the value for viscosity for air, it is slightly different to the values that we use. And you are right. This is by 2. This is the radius that we are talking about. So 8 times 1.825 times 10 to the power of minus 5, and then delta P is negative 7.78, and delta Z is this 130 millimeters, so 0.13 meter. Can you give me what the Q value is? Huh?
32.2.
That's not at all what I have, so could you double check? Second.
1.89.
Am I doing something wrong, or this is also not the value that I have?
8.0.
8, yeah, that is what I have. Second, 8 point.
8.044 10 to the power minus 9. No, minus 4.
Minus 4, yeah. So I have 8.05 times 10 to the power of minus 4. What is the unit here? Meter cube per second. Sometimes when I teach, this is, by the way, this is not new material. I teach this as part of a course called Engineering Mechanics in Biomedical Applications at SDSU. So I have done this problem. This is the 7th time that I am solving this problem. So I make the students, because some of them are undergraduates, do the dimension check and make sure the units are correct. I'm not going to make you guys
In
do
your
that.
class, you follow the SI system.
I do. They have hired me, so they need to follow my units.
So they, in the US version, they put all these FPS systems.
I'm tired of that, so I don't even go into that direction because I am going to confuse myself. So meter cube per second, but we have to convert this to liters per minute. So do that. So basically, you have to multiply by 60 and then 1000 for the conversion. 48, yeah. So 48 liters per minute. So basically, you see that the pressure drop of negative 7.78 pascals, which generated a flow of 20 liters per minute in the full scale 3D, generated a much faster flow of 48 liters per minute. And it makes sense in hindsight, right? Because in the anatomical model, it has to go through all these topological deformations, all the vortices that are creating that negative pressure, stopping the flow. It has to overcome all those things. And over here, the same pressure drop does not have to counter any of those flow field artifacts. We can directly push the flow through the pipe. And as a result, the Q is almost double the magnitude. So, as a result, it doesn't really make sense to idealize a flow field because we are not going to get the results correct. On the other hand, what we were doing before, in the particle transport analysis, we already fixed the velocity value of the field. So once we fix the velocity value, the drag was more or less what would have been in the real case. But here is something else. Here we are using the pressure drop to generate the flow, and the field value changes. And it is not tenable in that sense. Does it make sense what I'm trying to say?
Goes for the decrease in the velocity because it is trapped somewhere.
So think about what is going on if the topology is complex. The flow is swirling, let's say, and that is creating some kind of backflow, right? And that is creating some trapping, some barrier towards achieving its full potential.
The unidirectionality is lost, basically.
Yeah. So let me write that down now. So from the theoretical idealization, we have Q as 48 liters per minute. In full scale anatomical CFD, we have Q as 20 liters per minute for SEM delta P. Why is that? So the CFD results are lower, or the full scale results are lower because number one, the recirculating airflow in the anatomical appendages is absent in the theoretical model. So if we were indeed trying to keep the same flow rate, so if we want to generate a 48 liters per minute flow rate in the anatomical model, we have to apply a stronger pressure drop to push that through. And number two, the vortex patches in the anatomical, in the physiological field create localized low pressure, let me borrow your terminology, low pressure traps that can slow the flow down. Or the Bernoulli's principle lovers might have issues with that particular statement. Pressure is low, then velocity is very high. That's what they understand, right? So let's not use that. So the low pressure traps that can create local barriers to the overall flux. Okay. Again, just to repeat, while trying to explore the particle transport, we did not have to worry about that because there we were fixing the flow rate, we were fixing the V fluid to make sure that the drag is realistic. Here we don't have that benefit anymore, and hence idealization does not work if we are trying to understand the fluid dynamics of the respiratory tract. It works if you are trying to set a final exam question for your undergraduate students. Then it works. Then you can let them solve this. They are happy that they can apply Virgil's law, and then still they don't get the answers correct. So then they are not happy. Okay, so the last thing for today would be to just introduce some elements of CFD which hopefully we would be able to do some of tomorrow. Uh, how many of you have? I know I already asked this question, but can you just remind me how many of you have run simulations? Uh, you have. You have. Anyone else? What kind of simulations have you run? Runs in systems. In what kind of? System. But what is your geometry? What problem?
Swan dimension. There is a sample that there is a swan inside.
I see.
And then we need to study the how the fertilizer pass through this one. And then we calculate the pressure and velocity.
So one thing it can be done, if it was actually done as is, maybe you form subgroups. What do you think?
Yeah,
So
yeah.
that like you can like divide yourself into 3-4 together, and then the guy who has done actual answers can take the industry and the.
So you can probably lead a team of like three or four.
You, Parimal, Rahul, and who else has done answers? In case he has done answers, he is now switched to the open form.
Okay.
And he has like basic ideas.
So you know them better. What their skill level.
Yeah, yeah. So anyway, you all among yourself organize into 3-4 groups, and then maybe in the cat lab they can sit together or in your laptop, whatever is the most.
So the plan for tomorrow is we are not done yet, and I still need to write
Yes.
some. But the plan for tomorrow is I would first like to run the simulation myself, but basically launch the simulation how it should be done, so that you have a first-hand knowledge of how it is supposed to be set up. And but I have already have the simulation files on that the .dat files on the folder. We can directly use that to do the particle training. But let's first finish up for today. So computational fluid dynamics. So people who raised your hands, do you guys use commercial packages or are you developing in-house codes? Commercial.
And you actually Rahul has did some course in MATLAB also.
In MATLAB. Okay, okay. And someone you are doing open form. Okay. You are doing open form, right? Yes, sir. Okay. So, by the way, one aside comment: the drop impact simulation that my student ran, I think he has used OpenFOAM as well because he is also learning OpenFOAM. So we just need to clarify that with him. Okay, so computational fluid dynamics. So we know that it is entirely based on the kind of spatial discretization. Like it starts from some level of spatial discretization. So the different kinds of spatial discretization techniques. Do they have any kind of CFD codes here at the graduate level?
Most of them are done.
Okay. Okay. So
mechanical we offer you MTech as well as these students also take.
Okay. So you know this very basics. So finite difference technique.
Chemical. Chinese side doesn't offer course.
So maybe graduation not in place.
Okay, but in MTech maybe they haven't done, but in chemical MTech also they offer.
Okay. 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 So in terms of the discretization methods, we know we have the finite difference technique. And the finite volume technique. And the finite element method. Now, in terms of the work that we are going to do, and it seems like people who have run numerical simulations, we are using commercial packages. So let me write down some common ones that people use or we are using. So ANSYS Fluent is something that I use in my group a lot. And then we have Console, OpenForm, Star CCM. Star CCM is, by the way, very popular amongst some of the other fluids guys in my department at SDSU. And Abacus. So each of them, they use different kinds of discretization. So for example, Fluent is building that, digitizing that geometry. For ANSYS, the other package that I wrote, ANSYS ICEM, that's where we are going to do the meshing. Number 3, we will simulate the inhaled flow field, the inhaled airflow field. So again, this is a decoupled system in the sense that we don't run particle as, so we don't run the simulations as a two-phase simulation. So if we had, then the particles would have impacted the momentum of the field around it. We don't. We first simulate the inhaled airflow field because the particles are considered tiny enough compared to the length scale of the flow. And then we do particle tracking. So this is like the lecture notes because this particular plane I picked it directly from the course that I teach, and we don't do particle tracking in that course. I just handle the flow field simulation. So after the flow field, we do particle tracking. So this is Lagrangian inert DPM tracking. And finally, we will do post-processing. So we will track some particle sizes, figure out how much of those particles are going to land at a particular site in the airway, and then we are going to go back to some research papers, similar to what we did with the theoretical work. So we derived some formulations. We eventually got to a point where we can use the formulation to derive what the particle transport trends are like, and that formulation was found to be in a paper that was published last year. We are going to do the same thing with the CFD work. We are going to run a simulation, do the particle tracking, and then compare our numbers with something that has been published. So in terms of the papers that you should look up tonight would be this. So if you go to the on the cloud folder, if you go there, look up this particular paper, two papers. So this is this one. So Basu, this is my paper, Basu Scientific Reports 2020, and then the first one, Akash 2023, Frontiers in Drug Delivery. So both are papers from my group. The 2020 paper was when I was still new as a faculty, and this 2023 paper was led by my PhD student. Do a quick read through because I think I'm eventually going to show some results derived in class here and found in both these papers. And of course, the 2023 one is a little bit more updated in terms of its techniques. So let's stop here. So we are going to start with simulation tomorrow.
So we may meet tomorrow in the